amasomero gunagali mu kikomera abasomesa be tulina bakugu mu baana abaana tubaliisa bulungi nnyo munnange tulina main campus Buddo Naggalabi nga bwakayisa Buddo Junior.
Weewaawo akadde keeko essaawa ziri 9 mu kaseera kano tubeera tuzze nga tugguse bumale ku TV zammwe okubatuuzaako puroguramu yammwe eŋŋanzi eyitibwa BBS somera mu ddiiro lyo. Omuzadde yenna ali ewaka ng'omwana obadde okyalina emirimu gy'omutisse, nkusaba omuteeketeeke omugambe nti asooka agumiikirizeeko ko omusomesa Guse ate ajje asomere wamu naffe. Njagala okwebaliza ddala bannaffe abateekamu ensimbi Maryland Schools, Green Hill, Gombe Junior Secondary School, Gombe Junior Schools zonna bakwano baffe abatuyambako okutereka ebyo bye tuba tusomye aba BIC abatukolera penny yaffe n'eŋŋanzi Big Crystal. Mwena tubebaza nnyo olw'omulimu ogwo gw'ettendo gwe mwakakola so far. My dear candidates, I want to welcome you to today's program. I hope that you're ready with your pen and pencil, plus any form of writing material with you. I'm here again to discuss with the A-level students, Senior 5, Senior 6, this paper of physics, 510-1. First of all, I would like to wish everyone back there a happy celebration of the Uganda Matters. Today being 3rd June, I must say I cannot skip talking about this. I would like to welcome back everyone who has attended the virtual mass, the virtual service that has been airing on this station since the morning hours. We hope that we shall reflect on today's preaching from the different parts of the religions, that is the Protestants and the Catholics. And I finally would like to ask that the Uganda Matters continue praying for us. Well, last week I discussed another detector of the radiation, that is the Geiger-Müller tube. I gave an insight on its mode of operation, and I had promised that this week I'll go on and dissect more about this detector. However, before I continue any further, there is a question which came through my email, and I thought that I should talk about this. I should also share it with you out there. This question came in from a one Chimbugwe Peter from Kaliro. These are our brothers at, I think it's an NTC. They are teacher trainees. They are teachers in the making. One of them happened to have shared with me this question, and it got my attention that maybe I'd skipped talking about it, but there is need for me to indeed share it with the rest. It is a question to do with the applications of radioactivity, specifically in determining the volume of blood in the body. So, Peter, thank you very much for that, and of course, I welcome you to the show. I know you're tuned in with many other colleagues from that part of the country. So I want to share with you the question very quickly here. I want to write it down. The question was reading that a radioisotope of half-life, 2 hours, and activity and activity 2.88 exponent 7 disintegrations per hour was injected into the bloodstream of a cow full stop. Then a sample of 2.0 cubic centimeters of the blood from the cow, 16 hours later, was found to have an activity of 3.0 exponent 2 disintegrations per hour. Find the volume of blood in the cow. So, for those of you who have been following me from the start of this topic, you remember when I was talking about the applications of radioactivity, I mentioned an application that involved determining the volume of blood in the body. This question here presented to us involves a blood sample that was picked from a cow. However, the cow was first initially injected with a certain radioisotope of given half-life. So half-life is 2 hours, initial activity is 2.88 exponent 7, and then after 16 hours, they again draw back some of this blood and then discover that when they draw 2 cubic centimeters of this blood, its activity is now 3 exponent 2 disintegrations per hour. Number one, what we need to note about the question is that half-life is in hours, and so is the activity. Therefore, it means that I may not have to convert the units from hours. I'm going to be dealing with my time in hours, and then I can go on and find the activity. So what I'm going to do first is that I'm going to determine what would be the activity of the blood of this cow given the initial activity and under that half-life. Then after that, I am going to compare that activity with the activity of 2.0 cubic centimeters of a blood sample picked from the cow. Because remember, I told you that how the process is done. We first of all draw some blood and then mix it with this compound, which contains a certain radioisotope, definitely which is not harmful to the body. And then after that, we inject the blood back into the body. We then let the blood circulate in the body, mixing up with the one which is already present there, therefore giving room for this radioisotope to fully spread throughout the volume of blood in the body. Then after that, we shall draw some blood again out. Of course, that is after a certain period of time. It can be days, it can be months, it can be hours. In the case that we have, they drew a sample of 2 cubic centimeters of the blood from the cow, and then 16 hours later, it was found to have such an activity. So, half-life, T half is 2 hours. Initial activity, A naught, is 2.88 exponent 7. That is disintegrations per hour. Then, what else do I have? Activity of 2 cubic centimeters of the blood sample is, however, 3.0 exponent 2. That is 3 exponent 2. Definitely, same units, disintegrations per hour. Now, I want to first of all find out what would be the activity, what would be the expected activity of this blood that was injected with a radioisotope of this half-life after 16 hours. After t equals 16 hours, the activity, I would expect it to be A naught e power minus lambda t. And of course, this will translate into 2.88 exponent 7. That is the initial activity. Exponent minus, I'm quoting the definition of the decay constant lambda as natural log 2 divided by the half-life. So I'll have natural log 2 divided by half-life, which is 2 hours, then multiplied with the time small t, which is 16 hours. I mentioned already that since I have a half-life in hours, and then I'm also dealing with the time in hours, there is no need for me to go on and convert any of the units. Feeding that into my calculator should give me a half-life of around 2,500. Disintegrations per hour. So this is the expected activity of this sample, of this radioisotope after 16 hours. However, after injecting it in the cow and then drawing 2 cubic centimeters of blood from the cow, we're instead seeing that the 2 cubic centimeters have an activity of 3.0 exponent 2. Now, the question is, how much of the volume of the blood sample from the cow will be represented by this activity? Because we have the activity that is represented by only 2 cubic centimeters of the blood. Now, how about what volume is associated to this activity? I hope that my viewers out there, you're following me on this. This is a very good question. I think it's the only application which I had not given you a numerical example on, but thank God, Chimbugwe managed to share with me this, and I thought that indeed I must come back to this and share with you this interesting question. It's not technical at all, it's just a matter of understanding this application and the procedure of how it's done, of course, which I've started by talking about. So I want to go on and calculate the volume associated to this activity. So we're saying that, however, after 16 hours, 2 cubic centimeters of blood. Now, this activity is not just of the blood, but rather it is of the radioisotope that was injected into the blood of the cow. And of course, because I've talked about the fact that if you give it time, however much you injected this sample of the radioisotope in a small volume of the blood, but once we draw back the blood to the organism, in this case the cow, however, I mentioned that it can also be the human being, then this radioisotope is completely going to saturate throughout all the blood that is in the system. So picking 2 cubic centimeters, definitely, we know that there will be a sample of this radioisotope. So 2 cubic centimeters has an activity of 3 exponent 2. Now the question is, what is the volume? I'm going to assume that that volume is x centimeters cubed. What volume corresponds to 11.2500? disintegrations per hour. That is our question. And definitely the volume that is corresponding to this will be the volume of the blood that is in the organism. Why? Because this is the expected activity of the sample. However, if only 2 cubic centimeters, this is the expected activity of the radioisotope. However, if 2 cubic centimeters of a blood sample contains a certain amount of this radioisotope having this activity, of which we know that the activity of the entire radioisotope that was injected into the organism is supposed to be this, then definitely we can find out what volume would correspond to that activity. And that will give us the volume of the blood that is circulating in the organism. So allow me to move back to this side. I'm so grateful for the many emails and the different questions that people are sharing with me. In fact, it's not only this question that I've been shared with, but they've been sharing very many questions with me, and I've always been coming here and sharing them with the general public. However, I was just not mentioning who shared what and the rest. But I think starting from today onwards, I'll be mentioning the people who have brought us these good challenges and indeed sharing with all of us out there. So I'm going to use my simple mathematics there of a direct variation. However, I told you that when it comes to this step, people have very many ways of doing it depending on your choice of mathematics. Me, I'm a first principles person, so I prefer this. And definitely, if I was to write this in a formal mathematical statement, then I'll have 2 being equal to that, and then x being equal to this, cross-multiplying somewhere, and then ending up with the x cubic centimeters being 112500 times 2, then divided by 3 exponent 2. So this is the volume. When you do that math, you may correct me if I'm wrong, but I would expect that you get 750 cubic centimeters as the volume of blood in the sample. It's a very good one. We had skipped talking about it. And because of this, these are questions which people, if you check in the question bank, you may not come across, but they are very common in mock papers. And the mocks, the people who said the mocks are very, they are very technical. They always want to test you with those questions which may look like as if they are challenging, but when actually they are not. We usually set outside the norm during the mocks. So people will most probably find this in our reference books and then maybe also some mock papers. However, in the question bank, you may not find a number of this kind. So because of that, allow me share with you another number which I'm going to leave as an assignment for you, which is of the same type. But this one I'm not going to do, but it requires the same knowledge like what I've just demonstrated for you. So this is for you to try out. You will be sharing with me the possible solutions that you have come to. And this one reads that a small volume of a solution, I'm going to write it down very fast. It's your assignment. A small volume of a solution of a solution which contains a radioactive isotope of sodium a solution which contains a radioactive isotope of sodium had an activity of had an activity of 1,200 1,200 disintegrations per minute, full stop. When it was first introduced in the bloodstream, okay, this is the continuation. When it was first introduced into the bloodstream of a patient. Full stop. After 30 minutes, comma, the activity of 1 cubic centimeter of the blood was 0.5 disintegrations per minute. Full stop. If the half-life of sodium is 15 minutes, full stop, estimate the volume of blood in the patient. Estimate the volume of blood in the patient. Let me make good use of this space. So this, my dear colleagues, is yours to try out, and I hope you enjoy doing it. So I'm going to give you like 2 more minutes to write it down, but during that time, allow me now make a general review about the Geiger mirror tube. We mentioned that the Geiger mirror tube works on the avalanche effect. Why did we say it works on the avalanche effect? Because for it, the moment a single ionizing particle enters into the region which is containing the mixture of the argon gas and the halogen vapor, which in my example of the diagram which I drew for you was bromine. After causing ionization of a neutral gas atom, the electron will then drift to the anode while the positive ion will start making its journey to the cathode. However, we mentioned that the operating voltage of the GM tube is usually high, and this creates a very strong intense field inside the tube, such that it is going to give the electron a very large force, making it accelerate with a high speed, such that on its way, it causes secondary ionization. Due to this secondary ionization, we are going to have an avalanche or a high flow of electrons pouring onto the anode, and therefore constituting a current pulse across the resistor, if you look carefully on the diagram that we drew last time. So this current pulse that will pass across the resistor is going to lead to a voltage pulse which can be detected by a counter or a count rate meter. So the magnitude of the count rate detected by the meter will give us information on the nature, number one, of the ionizing radiation that entered into the tube. And number two, it also helps us deduce the properties of this radiation. So, at the start, I talked about a bromine vapor, which is playing the role of the quenching agent. I talked about the argon gas, providing us with the neutral gas atoms. I mentioned that the anode will always be made in form of a thin wire. And then we also have a Mika window. We then have an extra high tension field or a source of PD outside this gadget. So today, I wanted to first of all start by discussing the functions of all these parts in details, because this is a common question. Starting with number one, the Mika window itself. Then after that, I'll go on and discuss the graph of the count rate that is registered by the meter against the applied voltage across the tube. I hope that people are through with writing all of this down. I would like to thank all those people who went back and then they used the necessary resources that I gave last week in order for us to understand more about this topic. Very many people have appreciated what they have read in Tom Duncan. Others have used the internet, and indeed, they have managed to fully understand how the GM tube operates. But nevertheless, I'm here to share with some of us who probably still had some doubts. So, I'm not going to draw the diagram again. I'm under the assumption all of us have the diagram. But I'm going to put a very simple heading and mention functions of the parts. Of GM tube. Let me be specific. And number one, I'm starting with the thin Mika window. Because that is the first part. Now, this allows easy entry of the ionizing radiation into the tube. When you read in some reference books, they will also add on that this thin Mika window does not only provide an easy entry for the radiation into the tube, but it also prevents any external electric fields from interfering with the electric field that is present inside the tube. Remember, the Mika is made, it's an insulator of a kind. So if there are any external electric fields that may want to leak into the inside of the tube, because at the window of the tube, the material that the tube is made out is an insulator, that will be prevented, as we already know, depending on the knowledge of electrostatics that we get from 510-2. Number two, we have the argon gas at low pressure. Now, the argon itself may not be a big deal because, it is to some extent, but the key word which I'm going to emphasize here is the low pressure. Why should we maintain a low pressure of the gas? When the gas is at low pressure, after the ion pairs have been formed, this low pressure is going to ensure that the gas molecules are much further apart, and therefore the ions will be facilitated in motion but with minimum interference to the electrodes. If we happen to increase the pressure of the gas, then we are most likely to provide an external effect in terms of the force that is accelerating the ion pairs that are being formed. Yet we want the acceleration of the ion pairs to be solely due to the electric field. So that's why we always include this argon gas, which is at a low pressure. So I'm going to put this down that when atoms collide with a neutral atoms, ion pairs are formed, full stop. When the pressure is low, the gas molecules are much further apart, and ions move with minimum interference to the electrodes. When atoms collide with neutral atoms, when electrons. Of course, these electrons I'm referring to are those that were formed due to primary ionization. Then I've talked also about the halogen gas mixed with the argon. The halogen gas, halogen is a chemistry term, I think referring to the group 7 elements. And we say that the purpose of this is to act as the quenching agent. Number 3 is the halogen gas mixed with argon. Last time I hinted about the quenching effect, and I mentioned that when the positive ions are drifting towards the cathode, they come in with a lot of energy such that when they reach the cathode and collide with it, sometimes they have sufficient energy to knock out an electron, therefore destabilizing the atoms at the cathode, giving off a certain radiation, which can also now go back into the tube and then cause secondary ionization, giving us a false reading of the count rate, because now we shall be having a second avalanche almost happening. In fact, there's somebody who sent me an email and was inquiring, teacher, is it true that in the Geiger meter tube there are 2 avalanches occurring? I would like to answer that person right now. I'm forgetting the name. But we have the avalanche occurring at once. However, if not well controlled, if we do not include the quenching agent, we would be having a second avalanche effect, resulting from what? Resulting from the positive ions colliding with the atoms at the cathode and therefore knocking out an electron or destabilizing the atoms there, and then giving off a certain form of radiation, which will now want to come and again go through the same process of causing ionization, first with the atom that it will collide with, and then that atom producing electrons, which will further cause secondary ionization, giving us a false reading, contributing to a false reading on the count rate. So in order for us to avoid or to prevent second avalanche from occurring. That is why we put the quenching agent. And I also mentioned that sometimes this radiation may not be only due to the positive ions colliding with the cathode, but rather when the electrons that powered on the anode make their journey across the resistor such that a current pulse is detected, creating a voltage drop across the resistor to come back this side at the cathode. When they are coming back to neutralize the positive ions at the cathode, because it is after the electrons have been attracted at the cathode that the positive ions at the cathode will also neutralize. In other words, they will recombine, cancelling the effect of the two, the positive and the negative, thereby restoring the value of the electric field intensity of the tube back to the sensitive level in order for it to detect another incoming radiation. During that process, when these ones are recombining, still some energy is given off in the form of a radiation. Now, this radiation can again cause a second avalanche. This radiation that has been given off due to the positive ions and electrons recombining to neutralize the effect of the two, it may cause another avalanche through the same process. So in order for us to prevent this, that is why we said we must add a quenching agent, which is usually a halogen vapor. Either bromine, chlorine, you can think of all the halogens, but usually in practice they use the bromine vapor. And we say that what will this quenching agent do when that radiation has been emitted as a result of the positive atoms maybe colliding with the cathode, therefore destabilizing the atoms at the cathode, or as a result of the positive ions combining with the electrons such that they neutralize each other, producing that radiation. When that radiation is produced, instead of it going to cause a secondary ionization again, therefore leading to a second avalanche, that energy of the radiation that has been produced by either of those two processes will be used to dissociate the bromine vapor, or it will be absorbed by the bromine vapor and therefore it will be absorbed in the form of vibrational energy. It will just be absorbed by the bromine atom and then increasing its amplitude of vibration or dissociating it, like what the chemists would say. Now in that way, that radiation will have been prevented from causing the same effect as the ionizing radiation that entered the tube from a radioactive element. I hope I'm being clear on this, because I really want people to get this. That is the purpose of the halogen gas mixed with the argon, to act as a quenching agent. In case you come across a question which is asking you what is meant by the term quenching, in simple terms, we are saying that the quenching effect, or the term quenching, is in reference to the radiation that may result as the positive ions that were produced during the first ionization collide with the atoms at the cathode or recombine with the electrons that were transmitted through the anode, absorbing the energy from that radiation and then dissociating the bromine vapor or the halogen vapor inside. Now there we shall say that quenching has taken place. Further details of this, members, kindly, I beg of you that you use the reference books. Tom Duncan, I want to mention again that I highly recommend Tom Duncan. Go there, read through. The information that Tom Duncan wrote down is so much easy to comprehend. Roger Moncaster, you can do the same thing. Nelcon and Parker, especially if you have access to the 3rd and 5th edition, it is there. The internet is as simple as typing in Google, what is the meaning of quenching? Or define quenching. Or what is the purpose of a halogen gas or a halogen vapor in the Geiger-Müller tube? You're going to find very many solutions to that. But at the same time, I mentioned that you can also use YouTube. Or you can always come back and review our lessons on any of our platforms. That is YouTube and Facebook, as you're reading through your reference book. So allow me to summarize this to this, that this mixture forms a quenching agent which prevents secondary ionization, or which prevents a second avalanche from occurring. This halogen vapor acts as a quenching agent preventing a second avalanche from occurring. If we have a second avalanche occurring, now we shall have a false reading at the meter, at the retimeter. Moving on, let me also talk about the anode, which is in form of a wire. The second avalanche from occurring, or you can say which can prevent secondary ionization. Some people will say second avalanche or secondary ionization. Now, how about the anode, which is in form of a thin wire? This is the fourth part. 1, 2, 3, yeah. From electrostatics, we know that the charge density is inversely proportional to the area. So if I have my anode, which is in form of a thin wire, thin, of course, I'm referring to a very small cross-sectional area, then it is most likely that the electric field intensity along this will be very high and therefore strong enough to give us a large amount of force that will accelerate the produced electrons as a result of primary ionization. So, in simple terms, I want to say that this, due to its small cross-sectional area, provides us a very strong intense field inside the tube, i.e. provides a high electric field strength. So, I think those are the most crucial parts. However, before we go any further, let me also talk more about the dead time and the recovery time, because I had also hinted about this last week. And I mentioned that immediately after a pulse has been registered, there exists a period during which the tube is insensitive to the arrival of any more ionizing particles. And I told you that this period is divided into two. Number one, there is what we call the dead time period. And then number two, there is what we call the recovery time period. Very many people have also been contributing to this, giving me their findings on the meaning and definitions of these times. So today, let me further clarify about this. Then I'm also going to give you a few lines of a formal statement representing these two times. I mentioned that the process of the electrons moving from the anode to come this side and then neutralize the positive ions that are reaching the cathode usually takes some time. And the moment these electrons start pouring on the anode, the electric field intensity inside the tube is reduced to a value which is not sufficient enough to cause further gas amplification of the atoms, or sorry, of the ions formed as a result of an incoming radiation causing ionization. So during that time, the tube is insensitive. And that is the time which we are calling the dead time. Number two, we have also seen that, again, when the electrons reach the cathode to come in and neutralize the positive ions that have fallen on the cathode, still, not all of them are going to be neutralized at once. Now, again, during that time, and I said that this time is very, very, very small. When you read in Tom Duncan, they will tell you that that time is between 200 to 400 microseconds, both representing both the dead time and the recovery time. So dead time is for the electrons to drift to come to the cathode. Now, inside the tube, electric field has reduced. Then, recovery time, the electrons have reached the cathode. They have started neutralizing the positive ions. But we are saying that the electric field intensity will not be restored immediately because not all of them are going to be neutralized at the same time. It is also going to take some other small time. Now, that is what we are calling the recovery time. The tube is trying to recover. What is it recovering from? The dropped electric field intensity as a result of electrons being attracted or powering on the anode. Remember, the anode is positively charged and then the electrons are negatively charged. I showed this how the electric field in the tube behaves. It is running from that wire anode and then leading to the cathode. So when electrons start pouring on it, then the magnitude of the positive charge there reduces. And quickly, these ones are also attracted to the cathode. Why? Because positive ions were also drifting towards the cathode, number one, but number two, the cathode is positively, negatively charged, and then the positive ions are coming in. So, I'm going to write down and say that the dead time is the time when the tube does not at all respond to the incoming particles, i.e. the time taken by the positive ions to move far away enough from the anode for the electric field there to return to a level which is large enough for an avalanche to start again. Now, in my notes which I want to give, I want to use the statement that the time taken by the positive ions to move far away enough from the anode for the electric field there to return to a level which is large enough for an avalanche to start again. But exactly what time are we talking about? Remember, as the positive ions are drifting towards the cathode, also the electrons which poured on the anode are being attracted this side down. They are running through the external circuit to come and find the positive ions which are going to land on the cathode. So in my explanation, I'm using that view because I'm under the assumption that that will be easier for us to comprehend. Then the recovery time, I want to mention that it is the second stage of the period of insensitivity of the GM tube. And during this time, pulses are produced, but are very small to be detected. In simple terms, it is a very short time after the dead time, during which the electric pulses are being produced, but are not strong enough to be detected due to neutralization by the quenching agent. So, in the recovery time, remember I've said that electrons come in, now they are neutralizing the positive ions. Then also the radiations that were produced as a result of these two recombining, or the positive ions hitting the cathode, such that they destabilize the atoms there, giving off another radiation, which can lead to a second avalanche. They are also being absorbed by the quenching agent. But the moment the positive ions start being neutralized, now the tube starts recovering in terms of electric field strength. But it will not come back at once. That's what I said. That's what I'm saying, and that's what I want us to understand here. It will take some time for all the positive ions to be absorbed by the electrons which poured on the anode, and then also the radiations that are being produced during this process of recombination to also be absorbed by the quenching agent. Because the moment the electrons start neutralizing the positive ions, the electric field intensity inside the tube starts coming back. It starts building to a value which is sufficient enough to cause more gas amplification, or to cause more acceleration of the emitted electrons due to any other ionizing radiation entering the tube. I hope that people are following me on this. So let us write this down. Important terms to note. Number 1 is the dead time. And we're saying that this is the time when the tube does not at all respond to the incoming particles. Why? Full stop is the time taken by the positive ions to move far away enough let me say that is to say the time taken by the positive ions in the process of the positive ions moving away from the anode, also the electrons that have been absorbed by the anode are now being transmitted to the external circuit, making their journey to the cathode from the anode. For the electric field there to return to return to a level which is large enough for an avalanche to start again. So, because of time, I'm not going to be in position to share with you what I had written down on the recovery time. However, I trust that people will base on my explanation of the recovery time and also on what they are going to read from the reference books and then come up with a formal statement talking about the recovery time. It is 4 minutes to 4 p.m. I would like to thank you for being very good viewers. Kindly, my dear candidates out there, the struggle continues. Don't give up. Keep using the reference books. Keep using all the necessary resources around us. And most importantly, stay tuned to BBS Telefina. Make sure that you're always following all the lessons. Keep in touch with the teachers through their emails, through the general email, someramudirorio@gmail.com, through my personal email, lutherken@gmail.com. May the good Lord bless you all and have a good night. Thank you.
Somera mu ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi tusomesa arts and sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisulo eby'omulembe, science laboratory, ssaako ne computer lab wamu ne